Okay, so welcome back, everyone. This time we need an advance applause for Ángela Capel for stepping in. So I think it's really brave. So Lootens unfortunately couldn't come, but Ángela Capel gladly agreed to give his talk. And it's a tricky topic. So Ángela, I should say, is working, for example, on dissipative many-body systems, Lindbardians, a lot of interesting things. But this talk will be on characterizing quantum phases in terms of symmetry breaking.
Okay, so thank you very much for the introduction. And thanks everybody for staying here until, well, the second to last talk of the conference. This is really nice. So yeah, this has already been said, but as you can see, I'm none of these people that appear in the first slide. So I was asked to chip in because Lootens had a last-minute problem and he couldn't come. Well, I'm going to try to do my best to tell you what this paper is about. So I'm going to be talking about entanglement and DMRG in the generalized Landau paradigm. And what this talk is going to be about is essentially phases of matter. And we are going to restrict to 1+1D models with global symmetries all the time. So phases of matter in these models, we know that they are classified by spontaneous symmetry breaking in the group G, and in the ground state down to a subgroup H with a Chuko cycle in the second cohomology H of H and U1. So when this psi is non-trivial, what happens is that we have a symmetry-protected topological phase, so an SPT phase. And if we do not impose any symmetry, what happens is that Hamiltonians that have a unique ground state are all in the same phase, essentially. So there's nothing to classify, essentially. But now, of course, I'm talking about classification of phases, and before I have to tell you what I mean by a phase, right? And there are many different ways to define phases, and I would say that probably the closest one to the quantum information community, which is really at the core of the conference, is that it has to do with the following fact. So two phases belong to the same phase. Two states belong to the same phase if and only if they can be related with a sublinear depth G-symmetric quantum circuit. So this is the definition that we usually take. What this means in particular is that we cannot create long-range entanglement with these kind of circuits and long-range order. And this means in particular that we cannot map GHZ states to broader states, for example. So this is something that is not acceptable. For example, if we additionally to that impose that we have a symmetry, G, like in this case, we cannot change the cohomology class. And this means, for example, that if we have an SPT class, we have a type of short-range entanglement, and we cannot change it with a circuit that is of this kind of low depth. So in another way that I can say this, that is maybe more familiar for the many-body community, is that if we have something like the picture that I drew there, if now we try to construct a path that goes from this Hamiltonian to this Hamiltonian, the path, as you see, at some point has to cross this line and has this part that I mark with a red cross. And by this, I essentially mean that the gap in this path has to be closed at some point. So this is how we classify phases, usually. Now, if we look at gapped Hamiltonians in 1+1D systems, which is what we are studying here, we know that MPS methods like DMRG and IDMRG and so on are the state of the art for finding and describing ground states of these Hamiltonians. And in particular, what they do is exploit the entanglement structure of these states to efficiently represent them. So this is how they work, essentially. However, this is like one line of research, but we can consider another line of research, which is the operator version of this. And in this line of research, we study matrix product operators and matrix product operator algebras in particular, which are used to describe symmetries and dualities in no locality. And well, they can systematically be used to represent operators in the lattice, essentially. So now we have these two different directions of research. And what they do in this paper is essentially merge these two lines of research to provide this result, which is the main result of the paper. And well, in a general way, what we can say is that if we consider now a 1+1D gapped lattice Hamiltonian that has a symmetry G, what they find is that there is always a unique dual Hamiltonian with a dual ground state and a dual symmetry, such that the dual ground state completely breaks the symmetry. Okay, so I will stop here a second because so that you understand more or less what we are saying. So what we are saying is essentially that we have our Hamiltonian, right? And well, this Hamiltonian can be mapped through certain duality that is in particular unique and conserves the same spectrum, which is really important because it has the same eigenvalues, to a dual symmetry and a dual ground state. And this dual ground state is totally going to break the symmetry. This is very cool because what this means essentially is that this dual ground state that we're obtaining in the dual picture is going to minimize the entanglement. And if we are minimizing the entanglement and we are using tensor network methods to compute something, that means that we are going to obtain something that is much more efficient. So this is the purpose of this work, essentially. And maybe to try to motivate why they did this, what we can do is take an example that appeared much earlier in the literature, and we can take, well, what is probably the oldest example of an MPS, which is the AKLT model in a chain, which is the one that I write here. And the AKLT model, is given by this expression here. It's a dimension 2 MPS, and the part that I write here contains the MPS matrices, which are just Pauli matrices, as I write here. And the boundary condition, B, is just one of these 4 possible boundary conditions, essentially. Okay, so what happens in this case is that the MPS tensors, and by extension, the boundary degrees of freedom that appear in B, transform in a particular way under the SO3 symmetry. So for example, if we take RA, as I'm writing here, and we, in general, look at this set 2 times set 2 subgroup given by the pi rotations on all the major axes, which are described by these elements here. So what happens is that what we obtain is that the entanglement degrees of freedom transform as Pauli matrices. And this is what we are representing with this picture. I hope that you're seeing my mouse. This is what we are representing with this picture. And in particular, what this is also telling us is that if we consider different AKLT states, then we can break the global set 2 times set 2 symmetry on the boundary. So this is very interesting because what happens here is that the boundary conditions B are all mapped into one another using the action of the Paulis on these entanglement degrees of freedom. Okay, so this is what happens in the MPS picture. So there's a lot of entanglement there, so to say. But now we can look at the other picture, at the MPO picture. And what happened is that, well, K and T from the AKLT, so Kenny and Tasaki, right after this other paper, found a non-local unitary duality transformation that maps the AKLT that I just presented before to something, to some other model that has a spontaneous symmetry breaking, where essentially the entanglement is totally destroyed. And this non-local unitary duality, is given by this unitary that I'm writing here. So if you see this expression, this is an MPO with open boundary conditions. And what is happening is, again, that all these MPO matrices, so all these O's are Pauli matrices, but now this is constructed in such a way that the operator is a diagonal operator. So now, if we look at what happens in the symmetry breaking ground state, essentially what happens is that these states are product states. So there's no entanglement there anymore. So if we now take the AKLT depending on B, we can see that it's actually given by this unitary of K and T applied to a product state. So essentially what we have done is we have started with something that had a lot of entanglement, and by dualizing, we have arrived at something that has totally destroyed the entanglement. So essentially the symmetry breaking that we had on the boundary before has turned into a spontaneous symmetry breaking now in the bulk of the state. Okay, so this is at the core of the motivation of this work. This is something that was known from before, and then this motivated that they thought, okay, maybe this can be extended to some more models. No? And this is exactly what happened. But before giving you the general result, I have to give you a theory of dualities that was actually introduced by the same authors of this paper and some co-authors. And this theory of dualities is essentially a collection of non-local transformations between equivalent Hamiltonians that satisfy a family of conditions, a family of properties. So the first condition is that they map always local generalized symmetric Hamiltonians with a symmetry C1 to local generalized symmetric Hamiltonians with a symmetry C2. And in general, C1 and C2 don't need to be the same, so they can be different symmetries. So this is the first property. Then the second property is that you don't want to have boring dualities in some sense, so you don't want to have constant depth circuits as dualities. So what they impose is that you need to be able to map local non-symmetric operators to non-local string operators. And then in this way, of course, you are ruling out these kind of circuits because well, you cannot construct these maps with constant depth circuits. Then one other thing that we can say is that these dualities are actually unitaries when we include the action on the boundary conditions. And in particular, they preserve the spectrum, which is something that is going to be essential for the main result, as you saw before. And finally, these dualities can be implemented as linear depth quantum circuits. So in particular, if we allow for some additional measurement, you can reduce most of these dualities to constant depth circuits, but well, we are not really interested in that, or they are not really interested in that. So let's assume in general that you have linear depth quantum circuits to relate different notions. So what we can also conclude from this theory is that all these dualities can be expressed in terms of MPOs, and they are totally independent of the model. And this is really interesting because, in particular, what this is telling you is that this is universal. This is independent of the model that you consider. Very good. So this is the physical intuition behind this whole duality theory and this theory of dualities that they constructed. But now if we want to put some math into this, what we can see is the following. So what we can see is that if you consider a model with a categorical symmetry C, the possible gap faces of this model are classified by a choice of a module category P over C. Okay? And this is something very abstract, but if you want to have some easy example in mind, you can think of the example that I was saying before. So this is like a generalization of having a subgroup and having a two cosicon, essentially, something like that. And in particular, if we consider an ordinary symmetry, this is going to be the case. So module categories are going to be reduced to that. Now, sorry, what happens is that the ground states of these models can also be written as MPSs, as I read there. And then in particular, this means that the classification can be done in terms of MPSs from this point of view. And as what happened with the AKLT example, we can also see that the symmetry typically imposes some conditions on the transformation properties of the entanglement degrees of freedom. And this, for us, will be shown by means of the generacies that will appear in the Schmidt spectrum. So this is what will happen in the next few slides, as you will see. Okay, so now we go back to the main result. And now, since I introduced a little bit more of math, we can write the main result in the following form. So what they have is that for every 1 + 1D Hamiltonian that is gapped and in a lattice and has a symmetry C in a certain phase P, so now we restrict to a certain phase, we know that there is a unique dual Hamiltonian with a dual ground state that completely breaks the dual symmetry. And then in particular, this implies a couple of things. So the first one of them is that since we have no symmetries left, the ground state has no degeneracy in the Schmidt spectrum anymore. And then this means that it minimizes the entanglement and the bond dimension. And the second property that we have is that the MPS tensors that describe the ground state are unconstrained to the symmetry. And this is really interesting because this is minimizing the number of independent variational parameters. So when you put these two things together, what you obtain is that the MPS description is now computationally much cheaper, and therefore you get some practical advantage in computational methods, which was part of the motivation of doing this. And one thing that is important to remark here is that even if the original model has an ordinary group symmetry, the dual symmetry can be something much more complicated, so it can be even a non-invertible categorical symmetry, so it doesn't need to be like a group anymore. And still, this is a very abstract result, so maybe it's a bit difficult to grasp what we are actually saying here. So what I'm going to do is show you a particular example in which this can be shown more explicitly. So in this particular example, we consider a Hamiltonian, that is the spin-1 Heisenberg model, so the part of the HI zeros, and now we add a perturbation that is given by these HI1s and these HI2s with some parameters J1 and J2s. And the reason why we are doing this is essentially because now we are breaking the SO4 symmetry that the Heisenberg model has into some symmetry that is the A4, so the one that corresponds to the rotation symmetries of the tetrahedron. We are doing that. And now if we look at the different information that we obtain when we modify J1 and J2, we can write, well, we can sketch this phase diagram that I'm sketching here, in which you can see that these are the different phases that you would obtain in this particular case. So here in the center, you have the case J1 equals J2 equals 0, so the original Heisenberg model, and this is an SPT phase. So this is why I'm writing it like this. And we also know that the SPT phase is stable under small deformation, so this is why you have a whole region around it where you still have the same phase. And the other phases that we will obtain, apart from this, come from obtaining the ordinary A4 symmetric phase, which is the part that appears here, 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 and here. And then the D2 symmetric phase, which is when the A4 symmetry is broken down to the Z2 times Z2. So these are the phases that appear in this particular model. And now we are going to see in a numerical way how we can visualize the theoretical result that I just told you about before. So now we are going to focus on each of the phases separately. And if we start with the easiest one, so with the SPT phase, the one that corresponds to J1 equals J2 equals 0, so we have the following. Here, in the first plot, we are plotting the entanglement spectrum corresponding to the original Hamiltonian, to the original phase. And here we are corresponding 7 dual models. Okay, so we now want to compare the original one with all these dual models. And what we can see is that here the original one has a twofold degeneracy. And this twofold degeneracy is given from the fact that the entanglement degrees of freedom transform as the two-dimensional projective irreps of A4, essentially. So now if you look at all these other plots, the ones that are going to give you the minimal entanglement in the ground state are shown like this and this. So it's going to be this rep psi of D2 and rep psi of A4 in principle. However, if you look at the colors of the plots, so these colors are not arbitrary. What this is telling us, all of them being with the same colors, that they all belong to the same block. So this is still containing some symmetry, some abelian symmetry. And therefore, it has multiple constraints on the MPS tensors describing the ground state. So this is actually not minimizing the entanglement. The one that is minimizing the entanglement is the rep psi of A4. And you can see that actually in the plot that I have here at the bottom, because here what I'm plotting is the memory required to store the ground state. And you can see that the case that is minimal is when you have this red arrow, essentially, which is the rep psi of A4. Okay, so this is what we can see in this particular phase. And now we can look at the two other phases, and we obtain something very similar. So if we look at the A4 symmetric phase, we start with a threefold degeneracy, as you can see here in this picture. And then what we can find is that in this case, the optimal dual model is rep of A4, and this is also corresponding to the plot that I have here for the memory storage. And finally, if we look at the symmetric phase, the case is a bit different because now we have some abelian group, which means that we don't have any degeneracies in the entanglement spectrum, but there are still redundancies in the MPS description of due to the symmetry. So here in this particular case, we see that there are several plots in which we have essentially the same height for all the Schmidt values, but we again have to look at the different blocks, and we see that the one that has less blocks is the rep of D2. So what we obtain is that in this model is it's the only model in which there are no redundancies. So essentially it's also the one that is optimal from the computational point of view. And something that is interesting here is that there are actually some dualities that increase the amount of entanglement. So not only don't decrease it, but actually some of them increase it. So this is very nice, right? We have constructed this duality that actually allows us to do some computations in a more efficient way because we have less entanglement. However, the problem is that there's no free lunch, no? So there's always some complication. And in this case, the complication comes from the fact that the categorical symmetries of the dual models do not live generally in tensor product Hilbert spaces. They are much more complicated. They behave like gauge theories with local constraints on the kinematical degrees of freedom. And there are also some consequences of these models that I'm going to skip in the interest of time. And there's some mathematical formulation that is very interesting in terms of fusion categories and module categories, but I'm going to skip it as well. And with this, I will go to the last slide, in which essentially what we have is that there is a commutative diagram that relates all these notions here. So there's an equivalence between Bone algebras, which are algebras of operators, with the symmetries that we have been describing during the whole talk, and quasi-particles that I haven't mentioned, lack of time. And these equivalences are given by the gap phases, the kinematics, and the edge modes that I was describing before. So they are represented with all these elements here. So this is the main outcome of the project that I'm presenting here. And then the outlook, well, there are many natural questions that arise from this talk. I guess the first obvious one is, can you extend this to higher dimensions? And well, in principle, you can, right? Because, well, the only thing is that you need to be able to consider higher forms of symmetries. And for that, you need more difficult category theory. But I know that the authors are working on this, so it's something that, well, is on the way. And something that is also very interesting is that here I'm talking about dualities between phases, but I'm not talking about the phase transitions, right? So it would be really nice to understand what happens at phase transitions with this kind of theory. And what the authors conjecture that what could happen is probably that you could see this theory as going to the phase transition from very different points, and then maybe if you could understand all these different directions at the same time, maybe you could obtain better results, better computational results as well for the phase transitions. And finally, I've been talking about global symmetries all the time, but well, they would like to be able to deal with lattice symmetries as well, like translations, reflections, or multiple other lattice symmetries, but they don't know how to do that. They don't know how to do that, so don't ask me about that. So, well, thank you very much for your attention, and I should say that, yeah, since I'm not an expert on this, I won't probably be able to answer any question. But you should send the questions to Lootens, sorry.
Thanks a lot, Ángel. So, yeah, so we can't really have a sort of a lot of complicated questions, but if you have some comment or maybe a question you think someone else from the audience can answer, we can try it.
Yeah, that would be nice. Yeah.
Discussion.
I have an extremely basic question. So in the title there was a generalized Landau paradigm. So what do they call a generalized Landau paradigm?
That's a classification of phases.
So in what sense is it generalized?
Oh, this.
I think it's not limited to local symmetry breaking. Like it's not you don't necessarily it's not characterized by a local order parameter necessarily, but you can have non-local
so
order parameters.
SPTs are included. So it's okay.
Exactly.
Yeah, thanks.
So you mentioned that one of the motivation here is that you want to find more efficient, numerically efficient tensor network method.
Yes.
Where you have this kind of symmetry dual model. I think in the history, people also use this incorporate symmetry into tensor network computation using some Clash-Gordon tensors. I wonder, compared to this kind of numerical method that's already incorporate your symmetry, how will this get a more efficient way to numerically study ground state?
So it's something different, right? It's something different. So I agree with you that, of course, these methods already include the symmetry. This is something that is a bit different. They really have a way to show that at least in these systems, there's always going to be one duality that is going to give you something that is going to be optimal. And as far as I know, at least this is what they tell me, as far as I know, this wasn't known before. But there's always one and only one that is going to give you the optimal way to do that. So of course I agree with you that some things have already been done before, right?
Thanks. You kind of map first to a different problem, right? So you go to this, you're looking at this dual Hamiltonians, and what you were referring to is like use the symmetries that you have in a given Hamiltonian, use these sort of imposing some symmetry constraints on the tensors to make the simulation more efficient. And here it's kind of a different approach where you have this versus non-local transformation that brings you to a more efficient or simpler problem to solve, maybe.
Do you know if the authors have an algorithmic way of finding what the dual model that's optimal is?
I don't know if I can say. I know that there's some work in progress. Okay. So maybe you all should send emails to Lootens about this.
So I thank Ángel again. Thanks for the discussion.